Welcome back to my YouTube channel. In last video, you seen some basic definitions related to electricity. That is the definition of electric current, then potential difference between the ends of a conductor, Ohm's law, mathematical expression of Ohm's law, that is V equal to IR. You seen these all things, and in this video you will see resistance, factors on which the resistance of the conductor depends, and after that resistivity, mathematical expression of resistivity of the material or resistivity of the conductor, and series combination of resistors. Let's see resistance, the definition of resistance. The electrical resistance of an object is a measure of its opposition to the flow of electric current. See the definition. The electrical resistance of an object is a measure of its opposition to the flow of electric current. Yes, see. The resistance is the measure of its opposition to the flow of electric current, or in other words, the obstruction offered to the flow of electric current by conductor. The obstruction offered to the flow of electric current by the conductor, he is called resistance of that conductor or resistance of that material. And you already seen the expression of resistance. The expression of resistance is R equal to V by I. Right? After that, we are having a resistivity. The definition of resistivity. Resistivity is the characteristic property of the material. Resistivity is what? Characteristic property of the material by which it resists. By which it resists the amount of current through it. It is very important definition, you remember. Resistivity is the characteristic property of the material. It is characteristic property of the material by which it resists the amount of current through it. By which it resists the amount of current through it. So these definitions you remember. After this, I go for factors on which the resistance of the conductor depends. So this is very important. See, factors on which the resistance of the conductor depends. It means on what factor the resistance of the conductor depends. See, the resistance of the conductor depends upon three factors. Namely, first one, the resistance of the conductor depends upon length of the conductor. It depends on length of the conductor. Second one, the resistance of the conductor depends on area of cross section of the conductor. Area of cross section of the conductor. Area of cross section of the conductor. Third point, it depends on nature of the material. Nature of the material used to make the conductor. And in some textbook they are given resistance of the conductor is also depends upon temperature. It also depends upon temperature. See, so this is a very important factors on which the resistance of the conductor depends. See, the resistance of the conductor depends upon these factors. First one, the resistance of the conductor depends upon length of the conductor. Second one, it depends area cross section of the conductor. Third one, nature of the material, and fourth one, temperature. Right? After this, I go for mathematical expression of resistivity. Mathematical expression of resistivity. See, you are having, yes, mathematical expression of mathematical expression of mathematical expression of resistivity. Mathematical expression of resistivity. See, the point number one, resistance of the conductor is directly proportional to length of the conductor. See, R is directly proportional to L. Yes, I'll write here first point. Resistance of the conductor is directly proportional to length of the conductor. It means if length of the conductor is more, then resistance is also more. If length of the conductor is more, there will be lots of opposition to the flow of electric current. Hence, I written here R is directly proportional to L. Second point, resistance of the conductor is inversely proportional to area of cross section of the conductor. Resistance of the conductor is inversely proportional to area of cross section of the conductor. It means if area increases, if area of the conductor increases, then its resistance decreases. And if area of the conductor decreases, that is area of cross section of the conductor decreases, then resistance will become more, that is the resistance will increases. Right? So these are 2 points you remember. That is, first one is R is directly proportional to length of the conductor and R is inversely proportional to area of cross section of the conductor. By taking these two equations, I will write form 1 and 2. Form 1 and 2. I will write R is directly proportional to L, length of the conductor, and inversely proportional to area of cross section of the conductor. R is directly proportional to length and inversely proportional to area of cross section of the conductor. Therefore, I will write R. And now I will remove this proportionality sign. I will remove this proportionality sign, and in place of proportionality sign, I will write a proportionality constant. And this proportionality constant is called rho. And this is a resistivity of the conductor. See, I removed this proportionality sign, and in place of proportionality sign, I written equal to, and after that proportionality constant. This proportionality constant is, so rho is the proportionality constant here, and this proportionality constant we are calling resistivity of the conductor or resistivity of the material. Yes, it is rho L divided by A. So I remove this proportionality sign, and in place of proportionality sign I written equal to rho, and this rho is called resistivity of the conductor or resistivity of the material. Right? So now see, I will write one sentence where yes, rho, this is called rho where rho is proportionality constant, known as resistivity of the conductor, known as resistivity of the conductor, right? So now I'll write R as it is. You take A in this side, so R into A is equal to rho L, or rho into L equal to R into A. So therefore rho equal to R into A divided by L. So this is the formula used to calculate resistivity of the conductor or resistivity of the material. You remember, rho is what? Resistivity of the conductor. Rho is resistivity of the conductor or resistivity of the material. So therefore resistivity of the material is equal to R into A divided by L, where R is a resistance of the conductor, A is a area of cross section of the conductor, and L is a length of the conductor. So this expression is very important, you remember. Now after this I go for SI unit of resistivity. I will go SI unit of resistivity. So I'll write here international system to measure the resistivity. Yes, I'll write here SI unit of resistivity. SI unit of resistivity, that is a rho. SI unit of resistivity, rho. See, we have the mathematical expression of resistivity. The mathematical expression of resistivity is rho equal to R into A divided by L. This is what? Mathematical expression of resistivity. See, the mathematical expression of resistivity is rho equal to R into A divided by L. So therefore rho I will write as it is. See, resistance of the conductor is measured in ohm. You see it is in last video. Resistance of the conductor or resistance of the material is measured in ohm. So I will write ohm here into area of cross section of the conductor. Area of cross section of the conductor is measured in meter square. Area of cross section of the conductor is measured in meter square, divided by length is measured in meter. Length is measured in meter. So therefore this meter and 1 meter for meter square get cancelled. Meter and 1 meter for meter square get cancelled. So therefore rho equal to, I will write ohm into meter. Ohm into meter. See, ohm into meter is the SI unit of resistivity. Remember, the SI unit of resistivity is ohm into meter. The SI unit of resistivity is what? Ohm into meter. So now, see, in this formula, yes, in this formula, I will take the value of R is equal to 1 ohm. R is equal to 1 ohm. Area of cross section of the conductor is 1 meter square. Area of cross section of the conductor is 1 meter square, and length of the conductor is 1 meter. Length of the conductor is 1 meter. Then equation 1 becomes. Then equation, yes, 1 becomes. This equation 1 becomes. So therefore I will write rho equal to R. R is measured in yes, ohm, that is 1 ohm it is. We took the value of R is 1 ohm into area of cross section. Area of cross section is yes, 1 meter square divided by length of the conductor, it is 1 meter. This 1 meter and 1 meter for 1 meter square get cancelled. Therefore, rho equal to, we are having here 1 ohm into meter. 1 ohm into meter. Remember, the resistivity of the material is said to be 1 ohm into meter. The resistivity of the conductor is said to be 1 ohm into meter when its resistance is 1 ohm, area cross section of the conductor is 1 meter square, and length of the conductor is 1 meter. Very simple definition. Very simple. See, the resistivity of the conductor is said to be 1 ohm into meter when resistance of the conductor is 1 ohm, area of cross section of the conductor is 1 meter square, and length of the conductor is 1 meter. Right? So, things to be remember. Things to be remember. And one more thing here. Yes, in the formula, rho equal to RA divided by L, you take only A equal to 1 meter square. Yes, in the formula, rho equal to RA by L, you take the value of area of cross section of the conductor is 1 meter square, and length is 1 meter. Then length of the conductor is 1 meter. Then rho equal to R into A, it is 1 meter square, divided by length is 1 meter. This 1 meter and 1 meter square get cancelled. So therefore, rho is equal to R into meter. R into meter. See, here resistivity of the material. Resistivity of the material is equal to resistance of the conductor. Resistivity of the material is equal to resistance of the conductor when area of cross section of the conductor is 1 meter square and length of the conductor is 1 meter. Right? See, resistivity of the conductor or resistivity of the material is said to be resistance of the conductor when area of cross section of the conductor is 1 meter square and its length is 1 meter. Right? So these things remember that rho equal to resistance into meters here. Rho equal to, we are having resistance into meter when area is 1 meter square and length is 1 meter. These things you remember. Next, after this we are having the combination of resistors. Combination of resistors. You know, combination of resistors, we are having two types. One is a series combination of resistors and another one is a parallel combination of resistors. See, in combination of resistors, we are having two types here. First, we are taking two or more than two resistors and which are connected in series. That is called a series combination of resistors. And after that, we are taking two or more than two resistors and which are connected in a parallel. And for that, we are telling a parallel combination of resistors. So I go for first one here. First one here. Series combination of resistors. Series combination of resistors. First one you take series combination of resistors. You take three resistors of resistance R1, R2, R3 which are connected N to M. So I am taking the three resistors here of resistance R1, R2 and R3 which are connected N to M. When resistors are connected N to N, for that we are telling series combination of resistors. We are taking three resistors of resistance R1, R2 and R3 which are connected N to N. Yes, sir. When the resistors are connected N to N, for that we are telling series combination of resistors. So I will write here, yes, consider consider three resistors of resistance R1, R2 and R3 are connected end to end, then it is called series combination of resistors. Then it is called series combination of resistors. See, I took three resistors of resistance R1, R2 and R3 which are connected end to end. Then it is called series combination of resistors. So see, I will take three resistors here. This is the one resistance of resistance R1. This is the second one of resistance R2, and this is the third one of resistance R3. So see, its resistance is R1, it is R2, and this is R3. Yes, these three resistors are connected end to end, and this is the point A, and this is another end. It is one end, and for this we are telling point A, and this is another end. For this we are telling point B. All right. Now these end points. These end points are connected. Battery. Yes, battery is what? It is a combination of cells. Battery it is called a combination of cells. Next one, plug key. It is closed. Plug key is closed, and yes, here emitter is connected in series to measure the electric current flowing in a circuit. Alright. See, we are having three resistors of resistance R1, R2 and R3 which are connected end to end. For this we are telling series combination of resistors. The end points of the resistors, that is the end points are A and B which are connected battery, and yes, plug key is closed. The electric current is flowing in this direction. So I is the electric current flowing in clockwise direction. I is the current flowing in clockwise direction. See, I is the current flowing in clockwise direction. See, one thing you remember here, when resistors are connected in a series, the current flowing in each resistor is same. We are connecting all the resistors in series, then current flowing in each resistor is same. Alright? But potential difference across each resistor is different. So here the potential difference is V1. Here the potential difference is V1. Here the potential difference is here, yes, V2. And here, yes, the potential difference is V3. Things to be remember, when resistors are connected end to end, or when resistors are connected in series combination, the current flowing in each resistor is same. The current flowing in R1 is same as the current flowing in R2, and it is same in R3. Right? The current flowing in each resistor is same, but potential difference across each resistor is different. So potential difference across R1 is V1, potential difference across R2 is V2, and potential difference across R3 is V3. Right? And see, here V is the net potential difference applied. V is what? It is the net potential difference applied. So therefore, I will write by Ohm's law. The net potential difference the net potential difference, the net potential difference, the net potential difference applied to the electric circuit, to the electric circuit is V equal to IR, V equal to IR. And you call this is the equation number 1. Now I will write V1, the potential difference drop across R1, comma V2, potential difference drop across R2 is V2, and V3, so V3 is the potential difference drop across R3. So therefore I will write V1, V2 and V3 are the potential difference, potential differences drops across R1, R2 and R3 respectively. So therefore by using Ohm's law, the potential difference drop across R1, the potential difference drop across R1 is V1, and this is equal to IR1. It is IR1. So why it is IR1 means because current flowing is same, and the potential difference drop across in the R1 we are finding. The potential difference drop across in R1. At the ends of the R1 we are finding. So hence I took here the value of V1 equal to IR1. Next, the potential difference drop across R2, P2 equal to IR2, equal it is 3. And the potential difference drop across R3 is V3, and this is equal to IR3, equal this is yes, equation number 4. Equal it is equation number 4. Now see, now I will write one sentence. The net potential difference applied here. V is what? The net potential difference applied. And the net potential difference applied is the algebraic sum of the potential differences drops across the R1, R2 and R3. Remember, the net potential difference applied to the electric circuit is the algebraic sum of the potential differences drop across R1, R2 and R3. So therefore I will write here yes, V is equal to V1 plus V2 plus V3. This is very important, you remember, right? V is the net potential difference applied. So net potential difference applied is equal to a sum of the PDs across the R1, R2 and R3. So therefore I will write by equation 1, 2, 3 and 4. 1, 2, 3 and 4 we get yes, you have to use equation 1, 2, 3, 4, right? So therefore in place of V you write IR. In place of V you write IR. In place of V1 you write IR1. In place of V2 you write IR2. In place of V3 we are having IR3. So I took the value of these all V, V1, V2, V3 in this equation. So now therefore IR is equal to, in this I is common, inside bracket I will write R1 plus R2 plus R3. Now this I get cancelled. So therefore R equal to R1 plus R2 plus R3. This formula is very important. When resistors are connected in series, then equivalent resistance is given by sum of all the resistors which are connected in series combination. See, So R the equivalent resistance of the resistors when connected in series, when all the resistors are connected in series. See, therefore I will write as R in the place of R, RS. So why in the place of R is RS means this RS is the equivalent resistance of all the resistors which are connected in series. So RS equal to I will write R1 plus R2 plus R3. Yes, RS is equal to R1 plus R2 plus R3. So this is the equivalent resistance of all the resistors which are connected in series. Right? So remember this formula. It is very important. Right? So now I go for some notes which are related to series combination of resistors. And these notes are very important because we are using these results in problem. These results in numerical problems. That is first one, note number 1. When two resistors of resistance R1 and R2, when two resistors of resistance R1 and R2 connected in series, then its equivalent resistance is given by RS is equal to R1 plus R2. See, remember the formula. When two resistors connected in series, then its equivalent resistance is given by RS is equal to R1 plus R2. Next I go for note number 2. Note number 2. See, R1, R2, R3 up to son, Rn, Rd, n number of resistors, connected in series. See, R1, R2, R3, R4 up to son, Rn, Rd, n number of resistors connected in series. Then its equivalent resistance is Rs is equal to R1 plus R2 plus R3 plus up to son plus Rn. So all the resistors are connected in series, hence its equivalent resistance is given by Rs equal to R1 plus R2 plus R3 plus up to son plus Rn. Next I go for third point. See, when R1 is equal to R2, R2 is equal to R3, this is equal to up to son E is equal to Rn. When all the resistors which are having the same resistance, see, these all are having the same values. That is the value of R1 is same as R2, R2 is same as R3, R3 is same as SR4 up to son Rn. Then equivalent resistance is given by Rs is equal to. Equivalent resistance is given by Rs equal to, in place of R1 you write R, in place of R2 R, in place of R3 R, plus up to son, plus in place of Rn you write R. In place of Rn you write R. Because Rn is also same as R. You say all are having equal values. R1 equal to R2 equal to R3 equal to up to son E is equal to Rn equal to R. Now this R plus R plus R plus R up to son plus R repeated how many times? N times. It repeated N times. So therefore equivalent resistance when all the resistors are connected in series and which is having the same values. See, Rs is the equivalent resistance of all the resistors connected in series and everyone is having same value. Then equivalent resistance is given by Rs is equal to N into R. So this is a very important formula to remember. Suppose if you connected 2 ohm 4 resistors in series, resistance of the resistors 2 ohm, resistance of the resistor is 2 ohm and 4 resistors which are connected in series, then its equivalent resistance is given by 4 into 2. That is equivalent resistance is 4 into 2 means it is the 8 ohm. Right. So directly we are using this formula to find the equivalent resistance when all resistors are having the same value. Right. So this is about series combination of resistors. And for parallel combination, you see in the next video. For parallel combination and numerical problems based on parallel combination, you see next video. So kindly share and subscribe my channel. Thank you for watching.